Hi, my name is Johann Max Rohr from the AEI in Hanover, and in this presentation I will introduce you to our work on experimental studies of fiber phase dynamics in the scope of the LISA backlink. First, let me introduce you to the backlink. As a result of the orbital mechanics, the angle between the inter-spacecraft laser links changes over time by about plus minus 1.1 degree. The spacecraft are designed to compensate for this by actuating the MOSA, movable subunits consisting of gravity reference sensor, optical bench, and telescope. The arm length changes as well. In consequence, laser frequency noise will limit the sensitivity of LISA, requiring techniques like TDI to extract the gravitational wave signal. To make TDI work, a phase reference between the two lasers in a spacecraft is needed, which is generated by the backlink. As a result of the motion of the MOSA, the backlink needs to be flexible. Therefore, a fiber connection is planned. A former experiment by our colleague Roland Flederman showed that this will in principle work, but is limited by STRAYLIGHT and requires post-processing. One of the primary contributors to scattered light in the backlink is fiber backscatter. Light sent from the TX laser, here shown in orange, is sent to the backlink fiber through several components to deliver the local oscillator to the adjacent bench. However, some of this light is scattered back in the backlink fiber and joins the optical path of the local oscillator, shown in green, which is provided by the adjacent optical bench. In consequence, reference and test mass interferometer will be spoiled by this backscattered light. The STRAYLIGHT-induced phase error can be approximated by this equation. It depends on the amplitude ratio of STRAYLIGHT and nominal beam and the phase of the STRAYLIGHT. Therefore, any effect on the backlink fiber will be visible in the backlink's performance. We tested the induced dynamics of this as a result of ionizing radiation, thermal effects, and fiber motion. To measure these dynamics, we use a heterodyne interferometer, and the measurements are performed in two steps. First, we perform a calibration measurement to obtain the heterodyne efficiency of the primary interferometer. This is done by interfering the local oscillator, shown in violet, with a beam coming from the fiber, shown in orange, and this is necessary to reconstruct the backscattered power. The second step is the measurement of the backscattered signal. The signal generating beam is now sent through the fiber in the nominal direction, and the backscattered light, here in the cyan dotted line, interferes then with the local oscillator. We also measure phase effects of the transmitted phase by comparing the transmitted signal to a reference interferometer. While measuring the backscattered light, we perform a temperature modulation of the fiber under test to accelerate the measurement and obtain a more conservative estimate of the maximum backscatter expected. Here is a time series with such a modulation applied, and we measure a peak backscatter of about 7.1 ppm. This temperature modulation also allows us to measure the temperature to phase coupling by comparing the measured phase signal through the fiber to the applied temperature. In the example shown here, we measure a temperature coupling of about 43 radian per Kelvin and meter. We did lots of measurements in terms of radiation, and we tested in total 4 different types of fibers to their response to the ionizing radiation in terms of the backscattered signal. Our first radiation campaign is already published, which you can find behind this QR code down here. I will shortly guide you through one of these measurements because all of them are far too much to speak about here, and will later give you a summary of our fiber properties. So let's have a look at this measurement here. These are the tests done with the LISA fiber candidate, the Nufern PM1060L, under gamma radiation. We tested different configuration, bare fibers, fibers with a splice connection in the middle, and a pair of shorter fibers connected by a connector to make the total same length as with the tests before. In the upper row, we show the measured peak backscatter, which fortunately remains constant with the increasing exposure to ionizing radiation. We measure a backscatter of less than 6 parts per million, which is about 1.5 parts per million per meter, and we see that the splice or connector within the fiber has a a slight increase in the signal as a result. Here in the middle, we observed the transmission of the fibers. For the bare configuration on the left, we see that there seems to be a decrease in transmission. However, when we are including the measurement errors and the other two configurations of spliced and connectorized fibers, we conclude that the transmission remains constant for this type of fibers. And down here in the bottom row, we show results of a distribution fit to our measured backscatter. This results in a mean backscatter value, and we also observe here that the mean backscatter remains constant with the increase in exposure to ionizing radiation, and that splice and connector once again show a slightly higher value. Let me quickly summarize the fiber properties. So we begin with the Fujikura fiber, which is heritage of LISA Pathfinder. This fiber type shows less than 7 ppm per meter of backscatter, a constant transmission, and fiber temperature coupling of less than 80 radian per Kelvin per meter. With these properties, we can make the backlink work. Then we tested the fiber core fiber, which is interesting for its polarizing properties. This type shows less than 18 ppm per meter of backscatter, but unfortunately a decrease in transmission when exposing the fiber to radiation, and therefore this fiber is not an option. Lastly, we tested two fiber types by Newfern with larger core diameters, and these show less than 1.6 or 2.3 ppm per meter of backscatter respectively, a constant transmission, and for both types low temperature coupling of less than 50 radian per Kelvin per meter. And therefore we can say the PM1060L is a very good choice for replacing the backlink fiber. Additionally, we also performed tests in backscatter and temperature coupling with LISA-like FIOSes, and we found that the values agree with the measurements we did in radiation campaigns, except for FIOS 3A, which unfortunately had a broken fiber, and all other measured values are relatively high, which can be explained by the overall shorter fiber length compared to the reference measurement. With the FIOS, we only have 1 meter of fiber, and the reference measurement used always 4 meters of fiber, and so we have in the end lower averaging and so are more prone to measurement errors here. In addition to the measurements in temperature coupling and backscatter, we did measurements looking into the response of the transmitted phase to motion of the fiber, and we used the setup for this. And here a pair of stepper motors moves a pair of lever arms in a sinusoidal manner, which in first order is similar to the motion we expect in LISA, and we attached a fiber to it. And here is an exemplary time series of such a measurement that shows a contribution at the motion frequency, and in this case at its second harmonic. Over many measurements at different angles and different frequencies, we find the motion coupling is less than 1 radian per degree of motion, and simulations show that this is fortunately negligible for the performance. Speaking of simulations, we applied the experimentally obtained coupling factors of fiber dynamics to a performance simulation of the backlink. As a reference, we show here the performance of the PIDS point design in green, which fulfills the 3 picometer per square root of hertz requirement when applying STRAYLIGHT correction through balance detection with a factor of 10. The performance goal of 1 picometer per square root of hertz, shown by the back line, is not fulfilled here, not even when we apply the same balance detection suppression by a factor of 10, which is shown here with the gray requirement line. The experimentally observed factors show an improvement of performance compared to the point design when we apply the parameters of the fibers we tested. And in the case of the Newfern PM1060L, here in light blue, we show that the performance goal is reached for the most part of the frequency band when we apply the same correction through balance detection as in the point design. With the parameters of FIOS we tested, shown here in the dark blue line, the performance goal is reached over the whole frequency range when applying the help of balance detection. The increase in performance here is mostly attributed to the overall total fiber length, which is shorter than with the comparisons before, but still, it's possible to reach the performance goal. Alternatively, we can also reach the performance goal without balance detection by applying the stricter temperature requirement, in this example here, of 0.6 millikelvin per square root of hertz, and this is shown in the orange line. And the dotted lines, even further in the range of fulfilling the performance, show simulations when applying the optical bench temperature requirement of 10 microkelvin per square root of hertz. And here we have also the comparison when adding in the motion to the simulation, which shows here again in the red dotted line that there's a negligible contribution. And with that, let me shortly summarize my presentation. I've introduced you to the backlink and how STRAYLIGHT and its dynamics limit the performance of it. Next, I introduced you to the backscatter experiment, which we use to measure set dynamics. Lastly, I showed you several measurements in terms of backscattered power and temperature coupling, which showed you that the backscattered power remains constant over increasing exposure to ionizing radiation. We applied this experimentally observed dynamics to simulate the backlink's performance, showing that the required and targeted performance can be achieved. Thank you very much for joining me. Here are a pair of QR codes leading you to the results of our first radiation campaign and the design of the free backlink experiment, which compares 3 different backlink implementations. Have a good day.